So we have been doing some experiments involving the stretching of springs, but they were actual objects. And now what we would like to do is turn our attention not to the object, but to the material that it is made out of. So I'd like you to consider instead not a steel spring, but a length of steel wire. So this one isn't helical, it's not been twisted up, it's just a long straight piece of wire. And we could hang something off the end of that, and we could see if it stretches or not, and it's going to stretch. All of those atoms are held together with their chemical bonds, and as we exert a force on the ends of the wire, it's going to stress those chemical bonds, and it's going to pull them apart ever so slightly. But if you look at the pictures, you can see that if I were to get one steel cable and hang a 5 kilogram mass off the end of it, then that would stretch that cable a little bit. And then if I get an identical cable and I hang an identical 5 kilogram mass of that one as well, you would expect them each to stretch by identical amounts, because they're identical cables with identical forces on them, made of identical material. You would expect everything to be the same. Now imagine that if I just place them side by side, so that the two pieces of steel cable are actually touching each other. Now, my two pieces of steel cable between them are supporting 10 kilograms worth of mass. But really, is there any difference between two separate cables, or if I were to just kind of melt them together slightly so that I had the same amount of steel, but now I've got it in a cable that's twice the thickness, well, twice the cross-sectional area that it was before? I'm using this to kind of justify to you why, when we're talking about materials, we don't want to have to worry about how thick the piece of steel is if it is, in fact, the steel that we are investigating rather than the example of the steel for a particular object. Obviously, if I had an actual steel cable, I could go to town examining that particular steel cable. But it's more often that an engineer will be more interested in the properties of the steel itself rather than this particular example of steel cable that's sitting in front of them at that moment. So when we're talking about the force that's stretching a piece of steel, for instance, we're actually less interested in the total amount of force and more interested in the amount of force on every single square millimeter or square centimeter, or usually by convention, every square meter of the cable. And so what we tend to do is we would look at that 10 kilogram mass, but then we would divide it by the cross-sectional area of the cable that we were hanging it from, because then that will give us the force per unit area rather than the total force, which will vary from thickness to thickness, but will not vary from material to material. So the force per unit area has a name. It's called the tensile stress, in recognition of the fact that we are stressing the bonds between the particles in the material. Stress means to put under pressure, or in this case, tensile stress, to put under a kind of force that's pulling them apart. So that's referred to as the stress, and it takes the Greek letter sigma, which is kind of a 0 or an O with a little tick on the top of it going off to the side. And so you'll often see it written as sigma equals F over A. Just a little note about the unit. It's newtons per meter squared, but that's the same unit as we study in pressure, the pressure of the atmosphere and things like that. So that's been named for many years, many hundreds of years, and that's known as the Pascal. So the unit of stress is the Newton per meter squared, but that's referred to as the Pascal, which is a capital P and a lowercase a. Is that all we need to do in order to consider materials versus examples of the material? Do we need to do anything else? We've translated the force into stress. What else do we need to have a think about? So I'm just going to replace this one with a second thing to have a little think about. So let's think about the extension now. So if you take a length of cable and you stress it with a force and it gets longer so that it extends a distance x, well, if I were to take an identical piece of cable and stick it to the end of the first one and stress that with a force F, well, you would expect both lengths of cable to stretch by X. The first bit of cable will stretch by X, and then the second piece of cable will stretch by X. And that's because you can imagine the two bits of cable as being connected in the middle. And we played this game when we did springs in series, that the end of the top cable won't know what's pulling it down, be it the force directly or the force with a piece of wire in between. So both pieces of cable, when in series, would stretch by the same amount. Well, obviously, we don't really want to talk about two separate pieces of cable stuck to each other. We could just, again, talk about one long cable of length 2L, and we would expect that to stretch by 2x. So again, if we are considering the material rather than this particular example of material, we have to accept that when the material stretches, a longer cable will stretch by more, because every single one of those pairs of atoms along the entire length of the cable, all of those bonds will extend ever so slightly. If you've got twice as many bonds, you'll extend by twice as much overall. So it's not okay to just ask what's the extension. We need to ask how much did each separate meter of the cable stretch by. So again, we're going to have to change our language or change our variables from extension to what is known as strain, which I personally just find a really frustrating word because it's just a little bit too much like stress and I get them muddled up all the time. So see if you can work out a good way to remember it. Extension per unit length. The tensile strain is just the extension divided by the original length. And we've often measured the original length before we extend it. And usually we subtract off all the original lengths, the original length from all of the measured lengths. And that gave us our extension. All we're asking for now is that we, at the end, divide by the original length so that instead of a raw extension, we've got the extension per unit length. Notice that that is meters divided by meters, and therefore strain is a dimensionless quantity. It'll just be a decimal. You could multiply it by 100 and turn it into a percentage if you want to, but if you do, make sure you put a percentage sign on the end of it so that people don't think that the strain is just randomly 100 times bigger than it really is. That's tensile stress is kind of where we have shifted our force to. And tensile strain is where we've shifted our extension to. Sometimes these are called extensive and intensive variables. Extensive means that there is a dimension associated with it. So extension's an extensive variable. It depends on how big the object is. Force would be an extensive variable. It depends on what the cross-sectional area of the object is. But if we take away those extensions, if we take away the cross-sectional area and we take away the length of the material, then really what we're talking about is the force on a piece of cable that has a cross-sectional area of 1 meter and a length of 1 meter. Kind of cylinder of cable, 1 meter across and 1 meter, 1 meter in area, 1 meter squared in area and 1 meter high. Okay, so this particularly weird cable then would behave exactly like our F and our X if it happened to be this weird cable that's 1 meter in cross-sectional area and 1 meter in length. So if we did do that, we would expect a Hooke's law relationship. So we would again expect that we would get the whole F equals Kx thing going on. We just need to switch, like I said, from F, from the force to the stress, and from the extension to the strain. I didn't say, did I? The strain is represented by the Greek letter epsilon. So instead of F, we end up with sigma, and instead of X, we end up with epsilon, and we're still expecting the same Hooke's law relationship. It's just that the constant clearly isn't going to be the same, because F has been divided by an A, and X has been divided by a length. So when we factor those things in, our force constant K morphs itself into a new constant, which is always given the capital letter E. It's called Young's modulus, or the Young modulus, but I don't want you to think that young as in not very old. Young is a person. I'm not entirely sure historically why Thomas Young has got his name associated with this constant, because it wasn't his idea, and this analysis has been knocking around for at least 100 years before Thomas Young was born. So I'm not really quite clear myself on why it's called the Young modulus, but it is. And the word modulus is a really, really old word. It originally derives from the Latin word for measure. So that's all modulus is there for. It's just a historical term for this constant. Force constant would be a modern day expression. I guess we could call this the material constant or something, but historically it's called the Young modulus. The Young modulus is specific to the material itself and not to the dimensions of the material. So it doesn't matter how long the cable is. It doesn't matter what the diameter of the cable is. It just depends what the cable is made out of. So you can look it up. You can Google it or find tabulated data for the different Young modulus values for all different materials, in a way that you couldn't do that for objects, because there are an infinite number of objects that potentially could be made out of the material steel, but there is only one material that's made out of that material. So it's easy enough to tabulate specific examples of the material, of the different materials, but not all of the different things that could be made out of the materials. So you won't find tables of data for force constants, but you will find tables of data for the Young modulus. Note that the Young modulus is stress divided by strain, which is a unit of pascals divided by a dimensionless quantity. So the unit for the Young modulus is also pascals, just like the stress is. I could, at this point, break away and do all kinds of, look at this interesting thing that you can learn from stress and strain. But actually, I feel that these quantities are easily muddled, stress with strain in particular. And certainly using these algebraic quantities that we're not so familiar with, it's just easily jumbled in our heads. And so it might be a better idea to instead find some concrete examples of the Young modulus, and what better way than to actually measure it. Now, if we were in the laboratory back at school right now, I would have an experiment for you to do. It's hanging from the ceiling in A42, and I kick Mr. Mellings out every time I want to do the experiments, and we take over his lab and we hang things from a piece of cable that's attached to his ceiling. Obviously, we're not in school and we're not able to do that. And despite the fact that we will be back in school in just over a week's time, I didn't want to waste this opportunity for some learning now. Well, I'm quite happy to do the experiment when we get back into school, but I didn't want to break and wait just because we're a week off that. So I have got a video for you instead. I know, how exciting. Let me share my screen. Give me a second. Okay, on Google Classroom, there is an Excel download, and it has 3 tabs at the bottom of the Excel download. So the first one, YouTube, is where I want you to begin. And I need you to just click on that image. I think I put the direct link on Classroom as well, and it will take you to a 7.5-minute video by a lovely person called Mrs. Wilkins. and she is going to talk you through how to do the practical that we would be doing if we were in school this afternoon. Hers is mounted horizontally on a desk. Like I said, the one at Fallabroom is hanging from the ceiling, but it doesn't make a difference. The point is there's a length of wire with a weight hanging on the end of it, which is stretching the wire. I want you to watch the first 6 minutes of her video where she introduces you to the practical and she collects her data. And then when you've watched the first 6 minutes, before she does the big reveal and shows you the answer, I need you to hit the pause button. And then on the second tab of my spreadsheet, I have collected her data and I have tabulated it for you there. And I've put you a piece of PDF graph paper onto the classroom, but you could just use Excel to make a chart if you know how to do that. And I would like you to obtain the not force against extension graph. In an ideal world, you do stress against strain, but it's a little bit easier to not have to mess with the weird numbers that you'll have to plot on the axes. It's much easier to just plot mass against extension and then worry about the scale factors later on. So if you draw a graph of mass against extension and get the gradient of the straight bit, then you can turn that into a value for E, the Young modulus. Now, if you want to have a go at manipulating the equations yourself to turn mass divided by extension, which is what your graph's going to be, your gradient, your graph, into a Young modulus, then go for it. It's a really nice little activity for you. But if you get stuck or you don't know what you're doing, if you just click on the graph and analysis tab, which I'm not going to do, I have put all of the analysis on the next tab for you. Or you can return to Miss Wilkins and you can watch the last 90 seconds of her video and she'll go through it with you there as well. But the goal here is to obtain a value, a measured value of the Young modulus of the cable that she's using. And she's not actually using steel, she's using copper. So you're seeking the Young modulus of copper by experiment.